Hello, today we're going to be talking about the last element that we're going to add to our language P in order to make it the system that is pretty versatile, right? It's what we're going to end up just calling the system of first order logic. And that is a function. So let's take a quick look at that. All right, so here's some notes about functions and how they work and what they do and all that business. That there. And then we'll finish off by making some remarks about computability and how functions and how logic in general forms a basis for computation. So the best way to think of a function is as a little logic machine. If you have looked at functions in mathematics, right? So if you've had these in a math class or something like that, they're the same thing, okay? It's just that we're going to also use them here in our logical formal system as well, just in a very similar way to the way that you would use them in a mathematical formal system. We spent a lot of time very early in the semester saying, look, logic isn't math, they're not the same thing. But in this case, right, this little piece of it is very much the same. And the function is something that you might say, okay, well, cool that logic is using this thing that math uses, right? It's more accurate to say that math is using a thing that logic uses, right? A function is again, it's a logic machine. And it takes in, what a function does, it takes in some number of inputs, right? Could be any number, and delivers a single output, right? That's definitive of a function. And so you take the input or inputs, they go into the function, and then the function does whatever it does, depending on what kind of a function it is, and then that gives you the output. So in that sort of symbology there, the F, the italic F names what kind of function it is, and then the X names the input. Right, and then of course, since you get one output from this thing, we're going to end up treating a function as a logical individual, just like a lowercase letter in our system of formal logic. And so here's some examples of formalizing where you would want to use a function in your formalizing. So, for example, if you want to talk about Biff's oldest cousin, so if you want to say, like, Biff's oldest cousin jumped out of an airplane or something like that, then you'd have, blank jumped out of an airplane as your predicate, and then Biff's oldest cousin is going to have to go in there as the subject. Now, you could, under some circumstances, just simply put sort of a lowercase letter in there, but we can be more precise if we use a function. So the idea is you can use the C function, right, where the function C is the oldest cousin of whatever its input is, and then B as a lowercase letter is Biff, right? And the reason you want to use a function in this case, instead of just saying Biff's oldest cousin is like, the lowercase letter C, is because Biff is named in that, right? So it would just be weird. So this is where a function is a lot more appropriate, when you can then name Biff as an actual individual, because Biff is the input into this function. He's the input into the function that picks out somebody's oldest cousin, right? Now, you could talk about the biological father of Biff, okay, right? And again, you don't necessarily want to use a lowercase letter here because Biff is named in this definite description, right? But really, we want to name Biff's father, right? And so again, we can have a function. We can have the italic F function, which names the function the father of X, right, as in the father of the input, and then we'll have B being Biff as the input. You could talk about someone's twin sister. Okay, here what's going on is you've got a quantified over individual, someone, some existential quantifier, somebody's. Okay, and so what you have, there exists an X, such that, again, if you want to say someone's twin sister jumped out of an airplane, right, then you would have to say there's a predicate, capital A. So for all of X, capital A, T, function T, input X. Okay, so the T function, the italic T names the function the twin sister of, and then X names the input. Okay, and so there exists an X, that X goes in that input, right? Somebody is, somebody's twin sister has whatever property we're saying they have. Okay, and of course, we're going to specify here that the word twin in this case refers only to conventional twins, that is not to triplets or quadruplets or anything like that. We can represent that, it just gets messier and more complicated. And then finally, we could talk about everyone's favorite game show host, Steve Harvey, I'm guessing, right? And of course, in a universe of discourse that includes only people, it looks like this. It looks like we say for all of X, right? Something about, again, if you want to say everyone's favorite game show host jumped out of an airplane, right? That's, I hope he's wearing a parachute because, that would be tragic otherwise. But the idea is that we have G, right? The italic G names the function, is the favorite game show host of input, right? And then, of course, X is our input. So we want to say the favorite game show host of everyone, right? For all of X, right? So that's the idea there, is that what you're doing is you're naming a function and then naming some kind of an individual as an input, whether that individual is a variable or a constant, like say Biff. That's how it works. Now, in any situation where you suspect that some function names something that doesn't exist, right? So if you want to talk about Biff's oldest cousin jumping out of an airplane when Biff has no cousins, right? Then you have to use Russell's definite description format that we talked about in the previous chapter, right? Where you say, there exists an X, there's only one such thing, and that thing jumped out of an airplane, right? So that's the idea, and that will get you the right answer. That will avoid any troubles. So now it's time to talk about how functions work when they're on trees. The good news is there's really no difference, right? They make even less difference than the identity predicate makes. You just treat them like individuals, right? It looks a little funny. It takes a while to train your eyes to read a function as an individual because there's an extra set of parentheses, there's this italic letter in there, but really, the italics and the input, they just end up being a single individual, right? So say Biff's oldest cousin is Claire, right? Well, then the function that has, the oldest cousin function, and if you put Biff as an input, you get Claire as your output, okay? And so in a sense, that's equivalent, right? The italic C with Biff as the input function gives you just Claire, gives you just a lowercase letter. So again, these functions are going to act just like lowercase letters. So here's an example of a tree, right? It's a very, very simple tree just to illustrate this example. And actually, I'm going to want my little spotlight. Here we go. No, spotlight. Thank you. Okay. So if you look at this, universal statement here, so for all of X, f of X, right? X is an F. So everything is an F. That's what this says. And so we've just got another thing down here and another thing here and another thing here and here. So the idea is that once we're instantiating this for all of X, for all of X, f of X, is that you have to instantiate it for every individual, right? For every lowercase letter on your tree. And so that's the case. So because we have GAB here, right? You have to do it for A, and so that gives you f of A, right? You have to do it for B, that gives you f of FB, right? Right here. Sorry. And then if you also have to do it for function input A. Okay, so because that is here, right? We have this h f of a, right? So because f of a, because notice the function f when with a as an input is going to give you something. Okay, it's going to give you an individual. We treat this this function a input as an individual, and so we have to put then f, right? We have to substitute that in for the x, right? F function a input. So that's just a thing to be aware of, right? Is that it counts like any other lowercase letter in your tree for the purposes of, decomposing universal statements. And likewise, on the existential, remember the rule is that when you have, there exists an X such that X is an F, right? And again, we have this GAB here, and we have this HF with a C in the input. If we're going to instantiate this, which we do right here with this sort of FD, the reason we have to pick D here or some other letters, we can't pick A or B because they're already on the tree. Remember, the rule is if we're just choosing some arbitrary individual, it says there exists an X that such that X is an F. Call X, David or something like that, right? The idea is that we can't make it be A because we already know something about A, namely that A bears the G relation to B, Okay, we can't make it B because B bears the G relation to A, right, or is born the G relation by A, and then we know something about C, namely that it's an input in a function. Now this little italic letter here doesn't count as a lowercase letter for our purposes, so you could write F, capital F, lowercase f if you wanted, right? There's no rule against that. Again, the lowercase f is a constant. The sort of italic f names a function, and then C is an input. The reason we can't use C here is because C is used as an input in this function. So that's at least something we know about C. If we're going to be arbitrarily choosing an individual, right, when we say here, if there exists an X such that X is an F, we're going to say, okay, we have to use one that we don't know literally anything about, something that does not appear anywhere else. And as an input in a function counts as somewhere else, okay? But the whole italic F input C does by itself count as one single individual. Okay, so there we go on that one. All right, so in addition to that, I want to talk about sort of nesting functions, right? This is when we have functions within functions, because if a function can exist, right, and it's just the same as an individual, and if an individual can be an input in a function, well, that means a function can be an input into a function, right? If you just sort of think of it logically, right? And so let's see some examples of that. Again, since a function is an individual, that's just exactly what I said. There's nothing wrong with the function being an input in another function. So if you want to say the successor of the sum of x and y, right? You want to say something about that individual, because notice one thing will be picked out of the world in that way. You have s, which names the successor function. Okay, and as your input, you have the sum of, I have p for plus, right? The p function is the sum of, and we have two inputs in that function. You have two inputs, right? But it will give you one output. That's what summing does. It adds things together. So take any number of inputs and then you add them together. You'll get one output. Okay, and so the idea is that, say that x and y are like 1 and 2, the sum of 1 and 2 will be 3. Then the successor of 3, right, will be 4. And so this whole phrase here is equivalent to 4, right? It's equivalent to the individual number 4, right? So then not only can we have a function be the input in a function, but a function can be an input in its own function, okay? So a function can be an input in itself. And when that happens, we call it a recursive function, right? Something is defined in terms of itself, right? So if we want to talk about the successor of something, or even the successor of the successor of the successor, et cetera, the idea is we put this successor function as an input inside of another successor function. And so if x is, say, 1, for example, then the successor of 1 is going to be 2, okay? And the successor of 2, which is going to be this s here, is going to be, of course, 3. And so the successor of 1 is 3. And again, it picks out one and only one thing in the world. That's what's really important. Anything that picks out lots of different things, not a function. It has to take in any number of inputs, give you one output, and that is why it gets to count as an individual. Okay. So time for a little bit of nerd humor, actually. If you type recursion into a Google search, which I've done here, it says, did you mean recursion? Okay, and if you then sort of click on it, because it's a link, right, notice it's not spelled wrong or anything like that. Oftentimes they'll do that when you say that you've spelled something wrong or think you were really looking for something else. But no, if you type in recursion, it'll say, did you mean recursion? And so when you click on it, what it does is it defines a new search about recursion in terms of the word recursion. Okay, so it defines a new search in terms of it's nerd humor, right? They did this on purpose just to be funny, because believe it or not, there are nerds that work at Google. So there you go. All right, so now that we're talking about computers and Google and nerds and things like that, it's time to start talking about computing generally. And so this is where we start to get into a point that I really did want to make before the course was over. And that is about the nature of computing and what computers really are and what they really do at the most fundamental level. Because essentially what, a lot of people think of computers as, these machines that do math, right? That at heart, they all just do, they manipulate ones and zeros. People say this all the time. So, there's just all the ones and zeros in there. But look, there are no actual ones and zeros in your computer, right? Take it apart and look. right? You will not find a single one or a single zero, right? And if you like take apart your hard drive, you're not going to find any tiny little ones. You put a magnifying glass on, like, your disk there. Forget it if you have even a solid state drive or something like that, but take a microscope to it, look everywhere. You will not find any ones, you will not find any zeros. Here, though, you can see this is a portrait of a guy named John von Neumann, who is one of the people most responsible for the sort of architecture of the modern computing machine. And his portrait is made out of ones and zeros in various configurations, mostly zeros, it looks like, which is a little unkind to him. I think, he was intellectually anyway, he was very much number one in his own sort of time and place. So anyway, big time. But look, there are no ones and zeros in your computer. This is an abstraction. Okay, we could say that all that computers do is manipulate A's and B's. We could say they manipulate trues and falses, which is essentially what the ones and the zeros are supposed to stand for. Essentially, it's not true that computers just do math. All right, what's true is that they do logic, right? That they can be, and because they can do logic, they can then be made to do math. And at base, what a computer is, it's a logic machine. And we'll spend a little bit of time talking about precisely what kind of a logic machine a modern computer is, or at least an idealized kind of computer. And so in order to do this, we're going to talk about the NAND operator, a little NAND machine. And so again, you can think of NAND, in fact, you can think of all of the truth functional connectives, the AND, the OR, the NOT, the if then, the if and only if, the biconditional. You can think of all of those things as functions, right, that take a certain kind of an input and give you a certain kind of an output, right? So if you put any two sentences into, and connect them with an AND, right, then you're going to get one and only one output, depending on whether those sentences are true or false. So if you have two true sentences, the AND function is gonna give you as an output true, right? If you put a true sentence and a false sentence into the AND machine will give you the output false. Okay, and so that's essentially what's going on there. All of our operators and connectives are little machines. They're in some sense functions, right? And so what we can do is we can use a function called a NAND. Sometimes it's called a NAND gate, but function works just as well. And it's symbolized by something called a Sheffer stroke when we write it down in sort of logic notation. So NAND is short for not and. Okay, it's sort of a kind of portmanteau, I guess. And so if you want to say something like P NAND Q, right? So P not and Q, what that is written in our more familiar language here. It is not the case that P and Q, so not and, right? And so the symbol for that, again, is called a Sheffer stroke, and it looks like this vertical line here. If you have a fairly standard keyboard layout, if you look above your Enter key, like all the way to right, you've got kind of a backslash as opposed to a forward slash. You've got a backslash, and then if you sort of hit Shift and that key, you've got that vertical line. That's generally how you do that on your keyboard. But it's just a simple vertical line. It's called the Sheffer stroke. Sometimes I've seen there be like a little arrow on one side of this, whether to differentiate it from like a NAND versus a NOR or something like that. But in general, just take a vertical line. That's you call that a Sheffer stroke. That's a NAND. And so, for example, that means that in sort of our conventional writing, negation, right, P and Q, is equivalent to P Sheffer Q, right, where P and Q can be any sentence of a formal system. And so here's the interesting thing about the NAND machine, or the NAND operator, the NAND function, whatever you want to call it. The NAND can be used to do everything that the other connectives and operators do. So you can actually reduce all of the machinery of logic to a system that will just use one symbol, that is one function, right? And that's actually kind of fascinating. Here's kind of how that works. So here we have a kind of a diagram that you would have to do in electronics school, right? If you were talking about circuit design and sort of electronic stuff, right? This is how to make an electronic system in some sense that does, or a diagram of an electronic system that does logical functions. So the idea is that it's a sort of an input-output relation, okay? So the idea is if you want the NOT, right, you have some input A, right, that you put into, and this little sort of D-shaped thing here, that is a NAND machine. What it'll do is it'll take whatever its input is and will do sort of not and. And so what that means is that if you want to use if you want the equivalent of a not, right? If you want to say not P, what you do is you just take P, right? Whatever your input is. In this case, they call it A, but you take your input and you put it along with itself into a NAND machine, and then you'll get the appropriate output. You'll get the same output. So for example, if you want not P, you just put P into the NAND machine with another P. So P NAND P is the same thing as not P. Right? You can check that on a truth table if you want, right? Just remembering how to translate NAND into sort of not and. So if you want a conjunction, okay, you take your inputs A and B and you put them into a NAND machine and then take that output and put it itself through another NAND machine. So what that comes out as, you know, that P and Q is P NAND Q and P NAND Q, and then you put it together with another NAND. Okay, so those two inputs. So you can see visually how this diagram corresponds to this notation, right? And if not, you know, like pause it and really kind of look at it and say, aha, right? And then for a really nice drill, take a look at the OR diagram here, okay? And then try and come up with, you know, what that means, right? What that would look like in actual notation. And you can pause it here for, you know, for a couple of seconds to see if you can try and figure it out. Maybe bust out some scratch paper, right? And here it is. So P or Q is the same thing as P NAND P, NAND Q, right? So again, we have something and itself as an input in a NAND machine, something and itself as an input in a NAND machine, and then each of those outputs act as inputs in another NAND machine, and then it'll give you the output that is equivalent to P or Q, right? Now, of course, we have a NOR, which is not OR, right? That's this one here. Okay. And again, if you really want a great exercise, take a look at this. This is called an XOR. That means an exclusive OR, right? So remember, by default, OR means one or the other or both. Well, again, sometimes you want one or the other and not both, right? And we have ways of representing that in our, you know, logical formalism. But of course, this diagram here does it. And again, if you want a bit of a challenge, take a look at this and try and make the correct sort of, you know, formal notation using Sheffer strokes of what that really looks like if you write it down in our notation. And there it is. Okay, so P or Q and not P and Q is P Sheffer Q, Sheffer, Q Sheffer, P Sheffer Q. Okay. So we can walk through that. So we have, think of A as P and then B as Q, right? You could have just used A's and B's, right? It makes no difference. But the idea is you take an A and then A goes into input here, right? And so does, well, P and Q both go as inputs into this first NAND machine. And then the output of that, which is P NAND Q, that's this one here, this P NAND Q, this P NAND Q, right? This goes as an input in another NAND machine and another one of which goes with P, the other of which goes with Q. And then each of those things get put into a NAND machine. So this Sheffer stroke here corresponds, right, to this NAND machine, okay? This Sheffer stroke here and this one here correspond to this one and this one, okay? And then the idea is that, no, actually, sorry, this NAND machine here corresponds to this here, and that gets sort of duplicated. And then this NAND machine corresponds to this, and this NAND corresponds to that, right? Because that's the one where Q is getting in with P NAND Q, and P is going in with P NAND Q, okay? So there you go. That's you just sort of match up your NAND operators to your NAND machines one-to-one, putting the right inputs in there. It's really not so hard once you get the hang of it, but it's tremendously tedious, and no one should ever have to do this for any length of time. So not pictured in this diagram is if P then Q, but of course, because it's truth functional, you can do it with NANDs. And so that's P NAND, Q NAND Q, right? That's fairly simple. So then if you want to do if Q then P, it's Q NAND, P, right? And so then if you want to put those two things together as an and, well, you put, you know, sort of this NAND, it's NAND to the other one, right? And then this NAND, this NAND, the other one. And so essentially use this and structure over here for you know, if P then Q, and for if Q then P, and then you get the biconditional. That's the walkthrough on that one is done for you in the textbook with color coding, and you get to see lots and lots and lots and lots of parentheses, and boy, isn't checking those a great deal of fun. Like I said, no one should ever have to do this for a very long amount of time. I'm actually reminded of a bit of a funny story about all this Sheffer stroking. Um, there was a philosopher by the name of Donald Davidson, a pretty important philosopher of the 20th century, but I ended up studying his work a lot when I was in grad school. And once upon a time, he gave a talk at the University of Kansas in what's called a Lindley Lecture. The Lindley Lecture is a pretty famous lecture at the University of Kansas that happens once a year, and they invite some pretty big names to present some original work, some of the stuff they're working on, usually in ethics or value theory. Years and years ago, Davidson came and gave a paper called "Expressing Evaluations." It's very technical, actually. I'll hazard to say perhaps one of the most technical Lindley lectures, although I haven't read every one of them. I went to a number of them while I was in grad school, but I've not read every one of them. In any case, that paper that was presented at the Lindley lecture is printed up in this little pamphlet. You can order them from KU, and they'll send you the little pamphlet. I happen to have one. For the Davidson talk. There's also a book called Problems of Rationality, which is a collection of some of Donald Davidson's important papers on topics of rationality, and Expressing Evaluations is also printed in that book. And at the end of this paper, he does this analysis of the structure of evaluations. Again, it's horribly technical, and there's no reason to care a whole lot about it unless you care about these kinds of things. And it's a whole paragraph of something, and he decided to represent the structure with Sheffer strokes, right? Like instead of like some a more a standard notation that might be a little bit easier to unpack or understand when you look at it, because I mean, if you look at something like this here, like it's a little hard, with the parentheses and the vertical lines and it's visually hard to worry about. But it looks like this whole paragraph of nothing but parentheses and vertical lines and capital letters, right? And um, and it's just murder to try and parse out. And so in any case, the version of the paper that's printed in Problems of Rationality and the version that was printed up as the little Lindley lecture paper, that paragraph is a little bit different. And I recall sitting in one of my professor's offices in grad school a while, and we're both working through this, trying to decide which of them is the mistake, right? And it took forever. And I think both of our brains were reduced to mush by the time we were done with it. But we did discover definitively exactly what the error was. And to my shame, I don't recall which paper it was an error, whether it was the Lindley lecture or whether it was the Problems of Rationality. So I'd have to do it all over again at this point. But anyway, like I said, nobody should be forced to do that for a huge period of time. But if you work in circuit design, electrical engineering, you have to learn how to do it at some point, right? It's the basis of sort of everything that there is. So from an engineering standpoint, it's a lot easier to, instead of having all these different machines like the if-then, the or, the not, all these machines that do different things, from an engineering perspective, it's if you can make do with one machine that does the same thing and just make more of those and just put them in certain configurations, that's better from an engineering perspective than making lots of different machines that do different things. And so that's what the NAND does. It can do all kinds of things. So I wanted to show you one other thing, so I'm going to pull that up now. The kind of the system that I talk about in the textbook, which is called a Turing machine, right, is a system that essentially manipulates ones and zeros. And of course, in reality, if you build a Turing machine, it would have to be somewhat more complicated than that. At base, it can only it's still just doing various sort of logic functions, which can be represented with ones and zeros, or T's and F's, or A's and B's, or whatever. But here on the interwebs, here's an example of a Turing machine simulator. Right? In fact, you can look at the URL up here, and you can go and play around with this. For example, there's a program loaded here which does something very simple, and it checks whether the input is or isn't a palindrome. Remember, a palindrome is a thing that's the same backward as forward. And so notice that here, if this is our input, this is the machine's tape here. Notice this is not a palindrome, so I've put this input in there. It's not a palindrome, and so watch what happens when we run the program. And notice what happens is that the head will move, okay? And it will sort of, be able, it also, in addition to being able to write a 1 or write a 0, it will also be able to delete an input altogether or write down something that would make the machine go into a different machine state. And so this isn't as basic as the basic Turing machine. Like, it's not as basic as the TP5000 that I described in the textbook, but it's pretty basic. And so if you're curious, you can see the actual program here. Now, of course, this program is using a compiler, right? This isn't programming in machine code, okay? And so this compiler is probably several layers up from that, but still, right, because it's a simulated thing, it'll work just fine. And in fact, if you're curious about the syntax of that programming, so if you want to try and write your own sort of, really basic Turing machine program, you can use the syntax that's down here and some of the symbology that's used here. It's perfectly usable, although, again, very inefficient compared to a lot of the things that computers do now. So let's run the thing, okay? And you can see that it uses a procedure that it will then sort of write out a couple of extra characters, okay? So it has the capacity to write more than just a 1 or write more than just a 0. It can fetch a symbol and, but again, the instructions are very basic. And you can see that, what it did is, watch it one more time, is that it essentially checks to see if it sort of, eliminates symmetrically, then it's going to be a palindrome. If it eliminates asymmetrically, it isn't. And so that will essentially trigger an end state. So end, oh, asymmetric, and then it just erased everything and said, no, it's not a palindrome. Okay. And so this one, let's change the input a little bit. This one should go a little bit longer before it decides that it isn't a palindrome. Okay. So eliminate, symmetric, 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 and then asymmetric. So then it erased everything and was done, right? And so if we want like a really, really, really long input, basically what it'll do is it'll check the 1 that's on the left, and then it'll go to the other side to see if it matched, if it could eliminate asymmetrically. And once it gets over to here to the end of the tape and says, nope, the last thing was a 0 and the first thing was a 1, it'll just erase everything and say it wasn't a palindrome. So go ahead and watch. Oop, there it goes. Nope. So if we, again, wanted to, that should work unless that's, and I think that, we'll see. I may have put 1 too many or 1 too few zeros, but let's see. Great, yep. So that's, very nice palindrome. You can also, you might say, that's a lot of work for something so stupid, right? It is, but it's interesting work. So you could also look at, for example, a sequence machine, right? And again, this Turing machine is somewhat more sophisticated than TP5000 because what we've got some symbols which will run the machine into other machine states. Now, each of those machine states is itself defined, by functions that ultimately boil down to trues and falses. But there you go. So what this machine does is it generates an ever-growing sequence. It's a machine that will count. So it's another way. So notice I present one way in the textbook of making a Turing machine count. This is another way, and this is the way that Turing presented, and it requires a somewhat more sophisticated machine than the TP5000. But here goes. So if you want to run this program, again, you've got the E state, which is sort of, puts it into essentially switches its direction. And you've got these little X's that put it into a different machine state. And so it'll fetch an X and drop a 1, and then it'll go back to the beginning, and then it'll go until it sees an empty spot, then it'll drop a 0, and then X, 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 X until it hits another 0, right? And then we'll take each of those X's and we'll drop it off to the end of the tape, go back to the beginning, and it's going to go hit a 0, drop more X's, and then use the X's to deposit 1s until it gets to the end of the tape, right? And then it'll go all the way until it gets to the E, and that'll reverse its direction. And then it'll go till the end of the tape and start depositing X's, right? And so this will actually keep running. This one doesn't have a stop function. This will, if you want, simply run forever. But notice what's happened here. We have it gave us a 1, and then 2 1s, and then 3 1s, and then 4 1s, and then 5. And so it'll just keep on doing that forever and ever and ever and ever and ever until I just decide to pause it. And if you want to watch it sort of run one step at a time, you can step the program if you like to see this happen very slowly. And see which state, right, with a sort of previous, next state, current state that the computer is in at any given time, et cetera. So it's a fun thing you can play around with, and it lets you see a computing machine at about the most basic level that people generally do. But again, notice that what's going on here is that this is a compiler, right? This is something that uses, okay, uses these instructions to tell a computer to do a particular thing. Now, each of those instructions, of course, is going to stand for a whole nother function, right? And all of these commands stand for other functions, okay? And so, but at base, all those functions are just, all about, manipulating bits, or, not literally, but right, that when you write down what's going on, you'll write it down as, yes, they're manipulating bits, right? Ones, zeros, trues, falses, whatever. And so there you go. That's the nature of computing. That's what a computer is, what a computer does, and you never really do get to get away from various things. So, for example, if you look down at the syntax here, okay, we have sort of direction, right? L, right, or star, right? You like sort of move left, move right, or do not move, respectively. You have sort of new states here, right? And you've got essentially sort of instructions that are going to be like essentially if thens, right? So an instruction is very much like a conditional: if this then this, right? If this then this, if this then this, right? And then what you could do is, instead of specifying that in this thing, you could have a compiler that compiled all this stuff, where you could write it more or less in, you could just say, right, you could just like write some of these things more longhand if you thought that made more sense, and it could turn them into those symbols and then input them into the machine and then have the machine run this program. And so, but then you could make, sort of another thing. If you had a really complex function, you could just call it, well, let's call that really complex thing function f, and it does what it does. And then you could put that as an instruction in some other compiler. And that's the thing. You have compilers. It's compilers all the way down until you hit machine code, right? Which is really just the ones or the zeros or the trues or the falses, or again, however you want to symbolize that. So a good programmer is always going to have some idea of what their compiler is doing, but you never really do get away from the basic logical operators. You never do get away from the basic idea of if, then, and, or, not, etc. Right? So that's the nature of computing. I hope you found that interesting, and we're done with essentially functions, right? And so once functions are into our system, that's as complicated as we're going to make it. For the next time, for the chapter 17 stuff, I'm going to talk to you about some other ways we can make logic more complicated, but I'm not going to test you on any of that stuff, because that's just sort of looking ahead, right? Saying, now that you're at the end of a first year's logic course, what now, right? It's like, oh, rest assured, there's plenty, right? You've not even come anywhere near exhausting the wonderful world of logic. As much as you have done, and you have done a great amount, there's absolutely more, and that sort of more will happen the next time.